I had recently uploaded a video which was part of a class that I had taken recently to Facebook, and many of my friends had since asked me for a technical lecture or the technical know-how behind how to produce such a plot. Of course, there are many ways of doing this, and I have no way of claiming that the way I did it is the easiest or the best. The simple reason being, I am not an expert in these things. I just use whatever tools I have handy and put it together. However, the end result is not too bad. So let me try to explain to you how I produced this particular animation. Once again, let me rush in with the disclaimer that I am no expert and there definitely are other better ways of doing this. But well, I can only tell you what I know. So the tools that I have used in producing this particular video includes basically LaTeX, the document preparation system, in particular the Beamer package for LaTeX, and very much central to this is the use of the circuitikz module or circuitikz package of LaTeX. This is a part of the TIX, or an extension to be precise, of the TIX graphical system. This is a wonderful way of producing pictures in LaTeX, and I will hope to explain some of its features to you. I've also used rather extensively Python, namely NumPy and basically NumPy arrays and some of the Python string handling capabilities in order to produce the LaTeX code. Well, after producing the PDF file for the presentation, I had then, of course, recorded it using OBS, Open Broadcasting Studio software. But that's not an important part here. I'm just going to describe how I produced the PDF file using LaTeX, TIX, circuitikz, and Python in the first place. So I'm assuming that most of you are familiar, at least in passing, with basic Python syntax, and also you know what LaTeX is like. But I'm not going to assume that many of you know circuitikz or the TIX package in detail. So I will explain some of what I have used here. So let's take a look at the LaTeX source code for this particular thing that you have seen on the screen right now. And that looks like this. Now this might look quite daunting. In fact, let me just point out that the entire animation that you saw on screen essentially started, the code for that starts here with this begin circuitikz. We have gone into what is called the circuitikz environment, and this is rather long, with a rather long list of numbers which at this stage might look like complete gibberish to you, but it ends here in end circuitikz. So this is essentially one single picture which has been incrementally developed frame by frame, and that's how you see the video. But let me just try to sort of put this in, explain this by sort of breaking this up into bits. So this is basically where the code starts with this begin circuitikz. Well, American here just means that I'm using the American style symbol for the voltage sources and so on. Scale equal to 0.75. There's nothing much to explain here. It just means that overall whatever size the picture comes out to be, that has been scaled by a factor of 0.75. This additional thing that is after that, transform shape, is really a command which tells circuitikz not only do you scale the picture overall, you also scale the symbol. Say a resistance is supposed to occupy a particular amount of space in a circuitikz picture. If you just scale the picture without transforming shapes, the resistance symbol would stay exactly the same size as before. However, the other things, the wires, etc., will all go smaller. Now, this may or may not be what you want. Here I have wanted to also shrink all the symbols with the same factor. That's why the transform shape option has been used. Now, if you are familiar with LaTeX, you would know that all these things that I am writing here in square brackets are optional arguments which I am giving to circuitikz. So, if you look at the video once again, basically what it starts out with, okay, let's go to the beginning so that you can see how it starts. It starts out with basically this circuit diagram for the circuit which I am trying to analyze in this video. Down here in this corner, I have deliberately put a green rectangle around it so that you can see the circuit separately from the rest of the picture. And in the picture you have essentially the I versus V graph for the diode. Basically you have two curves, the static characteristic curve in blue and the corresponding dynamic characteristic curve in black. I'm assuming that you are vaguely familiar at least with these terms. Okay, you have two curves, one blue, one black in this picture. So to start out, let me just explain how I created this particular circuit diagram using circuitikz. Many of you may need to draw circuit diagrams, and circuitikz is a wonderful way of doing that. It actually gives you a huge amount of control over where to place your various circuit elements and so on, and you will find it rather surprising how easy it is to draw a circuit like this with just a few lines of code. In fact, frankly, effectively one line of code here. So despite the fact that the whole thing looked rather long with lots of numbers in it, don't worry about that right now. Let's just focus on this part of the picture, how to draw the circuit, and the code for that is just here. Well, the code is just this, sorry, wrong place, this one line. That's it. This one line draws the diode circuit. Okay, so let's just break this up for you. What does it say? It says /draw. Okay, you are asking it to draw. Now, these things in round brackets after that are coordinates. Circuitikz is based on TIX, which essentially uses coordinate geometry in a very big way. So here you are saying, take the point 0, 0. From that, well, the next point is 0, 2, so a point 2 centimeters vertically above. There's one thing, I'm saying 2 centimeters, but after all, the Beamer package scales things up in a way, makes it bigger. So, although I asked for a 2 centimeter height here, if this were really printed on using the standard article mode of LaTeX, this really would have been 2 centimeters. Of course, this wouldn't have been 2 centimeters here. There's a 0.75 scaling factor. So it would have been 1.5 centimeter if this were the article mode. But Beamer does its own scaling. So you may have to play around a bit before you can find out exactly how big you want your points to be, or how far apart you want your points to be. But here, at least nominally, what you're saying is from 0, 0 to the point 0, 2, which is up above 0, 0. What you do is, this simply says this is how you go from 0, 0 to 0, 2. 2, then within square brackets what you have put in is SV. SV is just short for sinusoidal voltage source. So all I am saying is between 0, 0 and 0, 2, put a sinusoidal voltage source. This, what you have here in equal to here $vi is simply a way of putting the label to the sinusoidal voltage source. And anyone who knows basic LaTeX would know that what you write in dollars in here is basically a LaTeX mathematical thing. V underscore I simply means V subscript I. So from 0, 0 to 0, 2 you put a sinusoidal voltage source. From 0 to 242, 4 centimeters to the right. In between, what you do is put in a diode, that's the D here. By the way, writing diode in full works, but once you get used to it, D for diode is pretty easy to remember. But in addition to that, you are saying V equal to VD, I equal to ID, within dollars. So what you're saying is, along with drawing the diode, you will also label the voltage across the diode and the current through the diode as VD and ID respectively. And then from 42 to 40, so you come down, you draw a resistance whose value will be labeled as RL. And when you write comma V equal to VR, automatically the voltage across the resistance will also be labeled with VR. Now, the American, which I put in here, essentially ensures that the style for writing these voltages conform to the way, the so-called American style, as opposed to the European style. In the European style, people use arrows to indicate voltages. Here you just have pluses and minuses, which are some which we know, which we are more familiar with. So after you go to 40, this double dash is simply, well, is not really circuitikz. This is plain TIX. 40 to 00 is simply draw a straight line between 40 to 00. So this one line is all you need to draw the circuit. Now, of course, if you have other kinds of circuit elements like transistors, etc., the drawing will be slightly more complicated. And if this had been a circuitikz lecture, I would have spent a lot of time trying to explain this to you. But let me just assure you that drawing circuits with circuitikz is really rather easy. And that's all I've done for this part. So if you look at the thing here, this is your 0 point. From that, between 00 to 02, you have put in a sinusoidal voltage source with Vi as a voltage labeled. Then you have a diode with the voltage labeled as Vd with the plus and minus clearly marked. Then you have an ID, the current, and then you have RL with plus and minus again clearly marked. Where did this green background come from? Well, all I did was use TIX again. By the way, circuitikz is built upon TIX, so whenever you begin a circuitikz environment, the TIX things are already available to you. So before I drew this, I put this here. I asked it to fill up. That's the slash fill. Green exclamation mark 30 essentially means 30% green, 70% white. If you don't say anything else, it's white. So it's 70% white, 30% green mixture. That's the color that you are asking for here. And then you are asking it to draw a rectangle with corners at -1.5, -1, somewhere slightly to the left and below your starting point of your circuit, to 5.5, 3. So these limits, the corners for the rectangles have been designed so that the circuit fits rather symmetrically between the 2 points. So all you really need to draw this part is some knowledge of coordinate geometry and some idea about where to put your circuit elements, and it should work out pretty fine. So the lower left corner of the video, which is static, is essentially just these two lines. That's it, nothing more. So let me just point out once again, this green background, that's a green rectangle on top of which I have drawn the circuit. Just one thing, the order of the lines here is important, because if I put the green rectangle after drawing the circuit, that is if the lines have been switched, then the green rectangle would have been drawn over the circuit, covering it up completely, and you would have just seen a solid green rectangle, not what you would want to see really. By the way, you can also use a semi-transparent option with the plotting, with this fill. So you could say fill slash fill within square brackets, put the color green exclamation mark 30, then comma semi-transparent, in which case even if you drew it after drawing the circuit will show through from below, and sometimes that kind of thing gives rise to rather nice visual effects. But at least so far, this is all you need for the lower left corner, the fixed circuit. What about the rest of the picture? Now, the rest of the picture starts somewhere else, and since you are drawing this in the same picture, the origin etc. would all have to be moved to some other place. For example, if you just notice that I have drawn coordinate axis here, and it would be nice for me if the origin For this coordinate axis they're called 0, 0, but unfortunately this point is already called 0, 0. So what do? Well, I fall back on TIX, which, let me remind you, circuitikz always has access to. So TIX allows you this begin scope, and of course there's an end scope somewhere. If you know your LaTeX, if you begin an environment, you have to end it, and you have to put this environment completely inside whatever other environment is in between. So the big end scope must come before the end circuitikz. But anyway, whatever you write within the begin scope, end scope in TIX is basically all the options that you are using here will apply to everything in here. So what are the options I have put in here? Simple, I've just asked it to X shift 8.5 centimeters, Y shift 5.5 centimeters. What does this mean? It means when I say 0, 0 inside the environment, after this, it will simply assume that after drawing whatever is inside is going to shift the whole thing in the horizontal direction, in the X direction by 8.5 centimeters and in the Y direction by 5.5 centimeters. Once again, let me warn you, these numbers would have been correct exactly if these had been the standard article format. Beamer scales up, and of course we already have a scale which is applicable to the entire picture. So when I say 8.5, it's really not going to be 8.5, it's going to be 8.5 into 0.75, or would have been that if the Beamer scaling, which is by some factor which makes everything bigger, had not been something which was in force. So now that you have that, what do we have? We have slash draw. Simple, you're asking it to draw. This is plain TIX. Okay, what do I want to draw? A line, of course. And here I have options for the line. Thick, of course, this is just a describer of what kind of line I want. I want the line to be thicker than the default line, so I put in thick. By the way, there's another option which is very thick, 2 words. Well, the next option is hyphen LaTeX. Now, we are using LaTeX anyway, so what is this hyphen LaTeX here? Well, this is an arrowhead designation. LaTeX, by the way, here is not the name of the document processing system. Here LaTeX really is the name of an arrowhead. So hyphen LaTeX simply means after you draw the line, at the end you put in an arrowhead. What kind of arrowhead? The special arrowhead which LaTeX supplies you. That's called the LaTeX arrowhead. You have seen this already, but let me just once I go back to the picture, you will see it again. Well, what am I asking you to do? From the coordinate minus 2, 0, of course, it's going to be shifted by 8.5 centimeters to the left, to the right, and 5.5 centimeters above. But let's keep that in the background for the time being. From the point minus 2, 0, so a bit left of the origin, to the point 4, 0, so a 6 centimeter stretch in all, you draw this line. That's double dash once again. Again, plain pure text, double dash for line. So from minus 20 to 40, draw the line, put in the LaTeX arrowhead, but you don't just stop there. You put a node. Where? You put a node at 4, 0, but you don't really write the contents of the node right there. A node is simply a way of putting something in a text picture. Once again, this is really not a tutorial on text. That would be rather huge. So all I'm saying here is the bare minimum that you need to understand what I've done here, done for the video. So your node below means, of course, not at 40, write whatever you want to write just below that. And what do you write there? Again, $V$ is LaTeX is for write V in the math mode. And so this is going to be a straight line from minus 20 to 4, 0 with an arrowhead, and just beneath the arrowhead you will have a label which is V. And every TIX command has to end with a semicolon. That's very, very important. If you don't put in a semicolon, LaTeX may spend a long time before complaining. So you will be stuck for a long time there. Okay, and then, well, this really is nothing but the horizontal axis for my graph. and the other one 0, 0 to 0, 4, the vertical axis. Here I did not bother to push it in the negative direction, because after all, current, as we know in a diode circuit, which is what we are trying to describe here, essentially flows only in the positive direction. There's hardly anything much to show in the negative direction. So I've drawn the vertical axis from the point 0, 0 to 0, 4, and at 0, 4, right next to the arrowhead, where the arrowhead is going to go, I've put in a node, but again not exactly there, to the left of it, which says $I. So just to remind you once again, when you have a node, you have two kinds of arguments here. The ones which you put in square brackets are optional. That's the standard convention for all of LaTeX. Arguments you put in square brackets are optional. Arguments you put in curly brackets are mandatory. So this has to be there. So if you have a node, if you don't have anything to put in the box, fine, but then at least you put in an empty pair of curly brackets. Otherwise, LaTeX is going to complain. So now that we have these two, let's go back and let's take a look at the video once again. This is the black line from -20 to 4, 0 with V as a label down here. The vertical line 0, 0 to 0, 4. So the axes are here. Fine. What else do we have? Well, we have quite a few other things in the picture, right? We have this blue line, we have this black line, we have these other axes. We also seem to have green and red circles. So where's the code for all of that? Well, all the code is really right here. Well, this big single draw here. So you have draw, then you have the options, thick, smooth, blue. So you have, and then you have plot coordinates. So please don't get frightened by the rather huge number of numbers that you see in here. Let's leave aside the question as to how I found out those numbers or how I managed to type them all in for the time being. You may have guessed I did not really do that by hand. I used Python to do that for me, to at least find out what to put in there. But basically the structure here is draw, slash draw, then some optional arguments, thick, of course, thickness of the line, blue, color of the line. So if you had paid attention, you would know that this is nothing but the diode static characteristic curve that I'm drawing here. That's the only thing in blue right now on the picture. So you have thick, smooth is an option, which will be rather clear the moment you understand what plot coordinates do. Well, what does plot coordinates do? And the syntax goes plot coordinates, then within curly brackets I'm putting in lots and lots of points. So of course each of this pair of numbers in a bracket, here is just -0, 0, then here is 0.623, 0.508 and so on. Each of this is of course a pair of coordinates of a point. So what I've done is put the coordinates of many points one after the other, and we have put everything in curly brackets to the plot coordinates command. So what is the LaTeX supposed to do with this? It's just supposed to plot a graph with these coordinates. And what it does by default is just plots those points and joins them with straight lines. The smooth option simply says that it's going to try to draw a smooth line in between and not draw jagged straight lines. So put in some extra points and draw a reasonably smooth curve. So that's all there is to it. So this command, although it looks rather horrifying, is really simply draw, thick, smooth, blue, 3 options. Plot coordinates within curly brackets, just a bunch of coordinates. How did I arrive at this bunch of coordinates, and how did I actually get this format in place, all these pairs of numbers with rather neat 3 digits after the decimal place in each one of them and so on? That is what I use Python for. So I will explain that in the next part. First, let's just try to understand, focus on what this is doing. This is just going to draw a smooth curve through these points. Well, the next one is also simple. It says smooth and thick, doesn't say blue, so it doesn't in fact specify any color. So this one is drawn with the default color, which is black. Then again, plot coordinates, a bunch of points, and this, I am assuming that you should have guessed by now, is nothing but this is the blue line is the first curve, and the one without the color specification is it's black. This is the black curve here, which is a dynamic characteristic curve. You want to plot straight lines, all you do is just give the two endpoints with a double, put a double hyphen between them. It will neatly draw the straight line. You don't have to specify anything about the intermediate points. Of course, that's something which anybody with any amount of geometry would know. 2 points define your straight line. But for curves, you have to specify points in between. Or there are other ways of plotting some special curves in TIX, but we are not going to go into those things. For example, circles, parabolas. TIX does a pretty good job of drawing them. If you just to specify, say for example, for a circle, you can specify the center, and the radius is going to do a wonderful job of drawing the circle. Parabola, if you say parabola from here to here with bend somewhere else. But these are not really the topic here. I'm not trying to teach you all of TIX. I'm just telling you that I drew this curve by using plot coordinates. I plotted this curve also by using plot coordinates. How I arrived at those coordinates? That's the Python part of the story, to be disclosed later. Well, after that comes this rather strange looking thing, only 102 to 105 within angular brackets. This actually is not TIX, this is Beamer at work. In the Beamer frame, you can put in many slides one after the other. And when you put a slash only command, it says that whatever is within this the curly brackets are following this slash only command is going to be shown only in slide number 102 to 105. So 102, 103, 104, 105, you're going to see whatever is here. So you're not going to see that at the beginning of the video. The video essentially is just one slide after another, and you can see here this is really at least 105 slides, because I've written 102 to 105 here. So there must be some other slides in between. So up to 105 from the 102nd to 105th slide, you are going to see this. Again, plot coordinates, some kind of coordinates, a green curve and a purple curve. If you paid attention while the video was playing, you would know that by now that the green curve is really a sinusoidal curve which goes down the vertical axis. And anybody who knows any electronics would know that's the input signal to the circuit, and the purple curve is the output to the circuit. But that is going to show up only later. So this 102 to 105, this part, these two curves are going to be plotted at the end, really, once the entire animation is played. But the slash only is the basic key to producing the animation. Slash only followed by angular bracket followed by frame number. It could be a single frame number, it could be a range of frame numbers as here, but a frame number, that's what you really need. Okay. Now comes a rather scary part for the rest of the thing, which is slash for each. Well, it sounds very much like a loop, right? Slash for each, and that's exactly what it is. Slash n, there's a LaTeX slash, the backslash, then there's a front slash, then the slash x, LaTeX slash, front slash, backslash y, front slash, backslash z, front slash, backslash w. Quite a mouthful. What this really is saying is, well, I am defining a lot of LaTeX variables here, assigning a lot of LaTeX variables here, slash n, slash x, slash y, slash z, slash w, exactly 5 of them. And you can see, peeking right under here, there is this line which says 2, 0.00, minus 0.5, minus 2.5, 0. So at least this is a loop where the first time the loop runs, slash n takes the value 2. Then the front slash here corresponds exactly to the front slash in this code. Slash x corresponds to 0. Again a front slash. Slash y corresponds to minus 0.5. Slash z corresponds to minus 2.5. Slash w corresponds to 0. So first time the loop runs, slash n, slash x, slash y, slash z, slash w have the values 2, 0.000, minus 0.500, minus 2.500 and 0.000 respectively. What about the next time? Well, 3, 0.190, minus 0.548, minus 2.548, 0.005 and so on. So now this actually goes on and on and on. Now, if these numbers had some nice geometric pattern, algebraic pattern to them, if they had all been, for example, in arithmetic progression, then I could have actually cut down on the code a lot. I could have just written down something like, say, slash n actually goes from 2 to maybe 99 or 100 here, or maybe 101. Should be 101, yeah, 2 to 101. So I could have just said 2, 3, dot, 101. That would have done. Unfortunately, the other variables I have here, x, y, z and w, these do not follow some neat arithmetic progression pattern. So I have to really write them all out. And you must have guessed by now, I did not, of course, type all of this thing in by hand. All of this was produced by Python. But now, after the 101, so this is the for each part. So this is specification of the values which the variables slash n, slash x, slash y, slash z, slash w take every time the loop runs. But what do you do then? Well, what you do is in the curly brackets right after that. What you do essentially is this. Okay, let's forget this for the time being. Let's focus on this. We'll come back and explain this later, although by the time I'm done with this, I'm pretty sure you will also be able to understand what's going on here. Only slash n. What does it mean? It means that whatever is being asked to be drawn here will show up only in the slide labeled by the variable slash n. Remember, the variable slash n is the very first entry in this list, and as you can see from the tail end, and you have seen at the beginning also, this actually goes 2, 3, 4, 5, 6, 7, 8, 9, 10 and so on. So what this is really telling you, only 2, that means only on the second slide show something, only the third slide show something, only the fourth slide show something. And what is it supposed to do? The draw line will, let's explain that later, but slash fill green slash x slash y circle 3 point. Perfectly clear what this does. It says that take the value of slash x and the value of slash y. These are the coordinates of a circle whose radius you are going to draw, and it's going to be a 3-point radius. This point is a unit of length which is used in typesetting and in LaTeX. So this is a reasonably largish dot. So this is, so what is asking you to do is from on the second slide, take the corresponding value of x and y from that line. That is your center of the circle. You draw a filled green circle of radius 3 points there. At the same time, fill purple slash z slash w. So remember, there were 5 variables: slash n, slash x, slash y, slash z, slash w. So x and y gave you the center for the green circle. Z and w gave you the center for the purple circle. And funnily enough, x, which is the x coordinate for the first circle, is also the x coordinate for this black circle here, whereas the y coordinate is the y coordinate for the second circle. Not really very difficult to understand where we are going with this, but this should make it even clearer. We are asking it also to draw a line from where the center of the green circle to the center of the black circle, and then to the center of the green circle. But where is the black circle? The black circle is exactly at the same x value as the green circle center, which means from the green circle center you go vertically up then you hit the black circle center, then you go horizontally until you go into the purple circle center. So let me just remind you of what you saw a while ago, or maybe let's play this a bit. And this of course is the green circle. The black circle which you can just make out here is sort of almost invisible because the 2-point radius which I've chosen for it is slightly bigger than the width of the line, and 3-point radius of course is slightly bigger again. That's the purple circle. That's at the near the beginning. This actually is really frame 2. There's 1 second has elapsed. This is really frame 2 of the animation. After, if I play this, notice what is happening. Okay, let me just stop you here. What has happened here, for example, you can see on a particular frame, maybe it's 2, 3, 4, 5. I can even count the number of dots here to figure out which frame this is, but maybe 10 or 11, frame number 10 or 11. That's the only /n where /n takes the value 11. Let's say the center of the green circle and the center of the purple circle are just x, y and zw, and vertically above there's this point, right? This point w. Of course, by some rather nice miracle, if you go vertically above it, you hit the dynamic characteristic curve, the black line here, and from that you are going there. So it's not really a surprise that when you go vertically up, at some point you are of course going to hit the dynamical characteristic curve, and it should not come as a surprise that I am actually reaching that point exactly. But how do I manage that? Of course, for that I have to calculate exactly what these coordinates x, y, z, w have to be, and for that again this Python. So that's the Python part of the preparation of the video, which I'm going to come to after this. This essentially is how I managed to get that huge 100 element list for the whole thing. Okay, but this is pretty easy to understand. Now you have drawn a green circle, drawn a purple circle, one for each frame. So as the frame changes, that green circle goes away, a new green circle comes in, and so on. But if you noticed, there are tiny green circles which are leaving a trail. Similarly, tiny purple circles which are also leaving a trail. How do you get that? Well, that exactly is what this other line does. Only /n hyphen 101. That means from frame number n to frame number 101, you draw the green circle, which is exactly the same coordinate, but make it smaller, 1-point radius, only 1-point radius. And since you're drawing this before you're drawing these, in the nth frame itself, say whatever value /n has, these 3-point radius filled green circle is going to simply cover the 1-point radius circle. So you're not going to see that 1-point radius circle in that frame. You will see it, of course, when the green circle moves away in the next frame. The big green circle moves away in the next frame. So that is why, as the video progresses, the green circle keeps on moving, the big green circle keeps on moving, and the trail of smaller green circles and the similarly smaller purple circles are left behind. I did not bother to leave a trail of the smaller black circles because they would have just followed the characteristic curve here and would have sort of merged with the characteristic curve. So just to point out, if I run the video a few more times, that's all that is happening, right? And in case you're wondering how we are going from slide to slide, in Beamer you can actually use an animate command which allows you to animate slide number this to slide number that. You can specify in the animate command with various other options like how much time delay to put between slides and so on. But I did not bother doing that for two reasons. One, the animate command form works well only in Adobe Acrobat Reader, and I don't really have that installed in my Ubuntu system right now. So my document viewer, which is Evans, does not really support the animate command. More importantly for me, I wanted to speak on top of the video and describe what's going on. This was for a class after all, and so I had to have a way of controlling the speed with which the points progressed, and because of that I prefer to just change from slide to slide with a key press. You just press the down arrow key and you keep moving from one slide to another slide. So every time I press the arrow key, the green circle, the large green circle, moves to its next position. Remember, this green circle at this particular /x/y has been drawn only for that particular slide, but there is another green circle just beneath that which is going to be uncovered when this moves away, and that's going to stay from, that comes into being in the next slide. That's why you cannot see the future ones here, and once it comes into being, it stays on until slide number 101. So that's what happens. So this is actually me pressing the down arrow key, trying to do it at a sort of reasonably uniform rate, and once this is run all the way, this is 101 slides gone, and the pause here is simply because I did not press the key to go to the next slide. I wanted to describe some other things, features here, and then I pressed the arrow and you went to the next slide, which was the solid curves. Where did the solid curves come from? Well, you may have forgotten all about them by now, but if you go all the way back up here, there were these, sorry, these, not these, I've gone too far. This is only from in slide number 102 to 105. Well, actually I could have just put it in slide number 102, but I was afraid that I may over press the key and cross beyond 102 and go on to the next frame altogether. I didn't want to do that, so I deliberately put this same thing on slide number 102, 103, 104 and 105. So even if I overshot one, I will still have the same thing. So the two solid curves, the green and the purple, which are really created just using those points that we had just used to draw the green points. So coming down, is there anything else to the picture? I don't think much. There's not much really, except for these two. Of course I could have put all this at the very beginning. Remember, these are outside the own/only specification, so these are there for all the frames. So these are really nothing but to access. Here you don't have the thick specification, so they're drawn with thin lines. Line with the LaTeX arrowhead, followed by, well, these lines are simply the auxiliary axis which I drew here. One t-axis going down, one v-axis going this way, another going here. So of course the origins of these have been shifted a bit. This one has been shifted vertically down, so the voltage goes parallel to this v-axis. The time of course has been shifted down a bit here. Similarly, here I've moved this a bit to the left, simply to give enough space for the black dot to go back and forth. The black dot basically signifying for a given input voltage how much is the current and so on, that you get from the dynamic characteristic curve. And here there is this purple curve which is drawn out, again shifted horizontally a bit. So if you followed what I've said so far, you would realize that I really used only very few elements of LaTeX in drawing this. I just used plot coordinates to plot the smooth curves here. Again, plot coordinates to plot this smooth curve and this purple curve here. But before that, I just used fill to draw filled circles. It's pretty straightforward actually. The only thing I did was use the only command to only draw things in certain slides and then take them away, so that you had moving things on the frame as I press the arrow key to go from one slide to another. The only tricky part now is how to write all those numbers in. And if of course this had been a small number of points and so on, I would have perhaps just written them in by hand. But that frankly is not a good option here. Writing down 101, 100 pentuplets of numbers. After all, you have to calculate these numbers also as well. And writing the 100 pentuplets is of course not child's play. But the great thing about this is, well, I could write a simple Python script which will actually produce exactly the numbers in this very format. So that all I have to do is take the Python output, copy it, paste it here. Well, actually I could have gone a bit further. I could have even used Python's own string manipulation techniques to simply write this code for me, all the numbers put in and everything. And so all I would have to do is just turn on my Python command, just run my Python script, and this whole code this LaTeX code will be written for me by Python. It's pretty easy enough to do. I didn't bother to do it for the simple reason that, well, I was not feeling like doing it. That's it. All I did was ask Python to produce strings of numbers like this, after the necessary calculations, of course, and then I just copied and pasted them here. So I essentially had to do one copy paste for this, another for this, 2, 3, 4, and one more copy paste for this. So basically one Python program which gave you all these 5 strings, I had to just copy paste 5 in 5 places. So despite looking rather impressive in the end, I hope it looked rather impressive, the amount of work which went into producing this file is really not that much. My explanation may sound rather long-winded right now, but that's because I'm telling you how to write these TIX commands and so on. If you already knew TIX and some LaTeX, following this would really be child's play for you. Okay, so if you are prepared to overlook for the time being the existence of these rather large number of numbers or pairs of numbers, coordinates, in this piece of code, I'm pretty sure you will agree that it's really not that big a thing. All I've used is a small line of code to draw the circuit, 2 lines here to draw axis, 2 curve drawing lines to draw the static and dynamic characteristics, 2 lines at the end for the input green signal and the output purple colored curve, and just this for each loop which essentially produces 1 circle per slide and keeps on moving these small circles, filled circles all over the place, so that you can trace out the input and output signals as they were varying. And there are 4 more lines here which essentially do the auxiliary axis. So the only tricky part left is to explain how I managed to use Python to create these rather daunting looking bunch of numbers. As I said, I used a Python program to produce these strings, just copy paste it from there. I will explain that, but this video is already rather long, so maybe I will, and the program will need some amount of explanation, so I will leave that for a subsequent video, hopefully coming soon. Bye till then.